Our final talk for today is from Todd Gamblin, and he will be giving us the Spack status and roadmap. So over to Todd.
All right. Hi, everybody. I guess this is an annual tradition now that we give a Spack talk at the Easy Build user meeting. So here I am again. I'm going to talk about some recent developments in the past year and then also some roadmap items at the end. A lot's gone on. Let's see. So I think people are familiar with Spack, but I usually include this overview for the Easy Build folks. It's similar to Easy Build in that we're building packages from source. In Spack, packages are parameterized, so users can easily tweak and tune the configuration. So you can just clone it and start running installations straight out of the Git repository. It's designed to be easy to install that way. It has a syntax for customizing installs. So instead of just installing a particular easy config name that has to come out of the easy config repo, for basically any package name, you can put a bunch of constraints on it. So you can install HDF5 at a particular version. You can actually choose versions that aren't there. They'll try to install at that version. You can specify a compiler, you can specify build options, inject flags, specify specific targets, and customize all that for your dependencies. Spack also generates modules, but it doesn't require them. You can load a Spack package without having to use the module system at all. We do that because it's sort of easier to get it working on both your laptop and the supercomputer in the same way. We allow virtual environments. I'll talk a lot about this. These are sort of becoming a platform for DevOps workflows. And we have a lot of workflows built around this stuff. So CI, container generation, and more things. Spack environments are, wait, where am I? Okay. The Spack community is growing. So we have over 6,000 software packages in Spack and over 900 contributors at this point. We broke 5,000 users on the doc site this year. So the community continues to grow pretty rapidly. And you can see over here, contributions to packages by organization. These are just the top organizations that have contributed to packages. Livermore is still the top contributor to packages, although I suspect that's because I update the copyright statement every year, and not because we're actually the #1 package contributor. Argonne, and it actually has 2 entries in here. This green one is just Adam Stewart. So it's actually pretty cool that we have Adam managing the package repo. A lot of these are other names that you'll recognize. And then this brown area is just organizations that, other organizations, and there's a lot of them. So it's cool to still see this sort of upward tilt on lines of code in packages. Spack environments are sort of a combination of what you would see with Rust and Cargo or NPM and say a Conda virtual environment. So they have a manifest, so we call it a spack.yaml, where you can list a bunch of packages that you want installed together. And you can include a bunch of configuration in there. It doesn't have to be, it's usually just written in line. And you can say how you want those packages built, what versions, what options you want on them, and so on. We'll concretize this whole thing and turn it into a concrete build spec and write out a lock file so that you can take this lock file and reproduce that build later. And so these 2 files sort of define an environment, and you can version them in a repo if you want. So you can sort of, you can have a whole CI pipeline built around a repository that contains one of these and have binary packages built on a regular basis for your Spack project. There's a lot of things built on top of environments like that. So we have external find, which allows you to go and query installed dependencies on the system. We'll stick configuration in your environment based on what we find. So it's sort of like we find compilers on the system, we'll find CMake, we'll find other pre-installed stuff. There's a testing framework. You can go and test everything in the environment by running Spack test. There's CI, we'll turn an environment into a CI pipeline. And there's containerization. So you can take an environment and turn it into a container that strips out basically all the build dependencies of what you built. And so it deploys just the application that you wanted in either a Docker or a Singularity recipe. This is Podman, uses the same recipe format as Docker. We released 0.17 this year, and it's probably the biggest Spack release that we've had ever. We sort of gutted the inside of Spack. We took the dependency resolver, which is sort of the core of the whole thing, and replaced it with a new one based on Klingo. This involved a lot of work around bootstrapping that thing from binaries because we wanted to maintain the property that you could just clone Spack from GitHub and go. And so now we have a C++ dependency because we need a fast solver to do all this stuff. And binary bootstrapping lets us get that running fast. If it works, you don't really notice it. It installs Klingo in the background. We have a really stripped down package for the solver. If it doesn't work, we'll bootstrap it from source, and it'll take a while, but you'll get a version of Klingo installed, and you can start running from there. The new Concretizer enabled this reuse feature that I'll talk about. I think, in particular at this meeting, people have complained a lot about changing hashes in Spack. This is the fix for that. Essentially, this means that Spack is now able to prefer the installed packages over just building from the configs directly. And there's a whole lot of other features. You can check out the release notes if you want to see all of those, but I'm going to talk about some of these. We did a survey last year, and we looked at the top wanted features, and essentially all of these, most of the top ones were tied to the new Concretizer. So reusing existing installs, the new Concretizer, and let's see, separate build dependencies. All of these were tied to the new Concretizer, and so we got those done in 0.17. The other thing that we did start that there's an initial PR for right now is Windows support. So Spack actually built its first few packages on Windows this year, and there's a pretty extensive PR getting reviewed that's going to be merged. We have Windows builds working in CI, and we're aiming to support a lot of these packages in the Windows environment too. This is really because we see people decide not to use Spack because other tools do support Windows. So we see people go and use Conda because it can deploy in all the environments that they want. And we have teams and we have industry contacts who want to use some of these scientific packages, say like, at their company, but their developers use Windows workstations. And so we're hoping, even though the current community doesn't seem to really care that much about Windows support, that this will continue to help us expand and will be looked at as a viable alternative to some of those other tools. The other kind of cool thing that this would let us do is, Spack has its roots in Nix and Geeks and sort of functional package management. It adds a dependency resolver on top of that. So it's sort of halfway between your traditional OS package manager and Nix. Nix and Geeks don't support Windows. And I think a lot of people have wanted a package manager like that in that environment. And so we're sort of hoping to get into that. One of the things that we added this year was more developer features. And so the main one was Spack Develop. Essentially, you can take an environment, and if you have a bunch of packages in your environment, you can activate it, you can add your application to the environment, and you can say, I want to develop like 2 pieces of that thing. And the cool thing about this is that then you can go and rebuild the whole stack with your tweaked develop version included. And so if someone hands you a Spack environment and you want to go and not just reproduce it, but work on it, you can do that pretty easily. We'll check out the source, you can tweak it, and rebuild the whole thing from that. We've seen teams use this to sort of, we have a lot of folks who are looking at integrating machine learning with traditional physics simulations. And so we have a team at Livermore that was trying to get PyTorch and Horavad and a bunch of ML stuff built along with their code on a PowerPC system with MPI. And so before they were using Spack with that, they spent a lot of time trying to debug build differences. Everyone had their own build script. It was horrible. I think everyone here at this meeting has heard that story. And after they started automating that, the team members can basically check out a repo with this description of their environment in it that specifies what compilers they want to use, all the different options on their package, and they can get set up in 20 minutes. The cool thing about that is they need their team members to be able to switch the versions around on PyTorch and to try new versions, try new updates, try hacked versions of it. And so they were able to be a lot more productive with this workflow. And so what teams had worked on this. They'd used Spack Develop for it, but this past year, we wanted to expand this to bigger codes. And so Marble is Livermore's, it's one of our multi-physics codes that does ICF simulations and things like that. The cool thing about Marble is that it was built from the ground up to have pluggable physics. And so you can choose whether you want to use Lagrangian hydro or Eulerian hydro in this code and swap out other physics modules fairly easily. But the downside of that is that the code is split into like 50 plus packages. And so they work on many of them at the same time. So you can see in this diagram, the core team sort of works on these top 4 packages. So Miranda is the Eulerian package and Blast is the AL or arbitrary Lagrangian Eulerian package. EXO is sort of the infrastructure package on top of that, and Marble ties it together. They have a bunch of packages that they also work on that are not theirs. And so they'll check out their repo. They might do a pull request to GitHub or to another internal Livermore organization, along with pull requests to the internal packages. And they want to keep that development synced over time. What industry seems to be doing to solve this problem is using monorepos, where they can basically keep everything versioned as one thing over time. We don't really think that our teams will adopt that, or that in the broader open source community that people will build like a big monorepo for literally everything. Managing permissions is hard for that. The timescales of development for the different codes vary, and one team might be on an old version of a dependency while another one might be on a new one. And that sort of independence is important. They had sort of a custom makefile based build system that handled some of this. It didn't provide the flexibility they wanted for versions. So essentially they're customizing makefiles over time to sort of have a mini package manager. It's probably the coolest and most horrible makefile based build system that I've ever seen. But we wanted to replace that sort of workflow with something that would work for the team. So Spack environments seemed like a good way to do this. What we were able to do is we added a few features like Spack develop. The main ones were Spack develop and Git support to environments. And so what you can do now is in your environment, you don't have to just specify a version in the package. If the package has a Git repository, you can say, I want to check it out at this particular commit. And we go and do the logic internally to relate the Git commit to tags in the repo, try to figure out what version it would be, and use that to build it with a Spack package. Essentially, the trick there is that Spack packages are templated, so you can build them with lots of different versions. We have to convert the Git commits to versions to do. So we're doing that now, and the team's able to basically pin things to the degree that they want. They wanted to be able to pin things down to commits. They can have a file like this that covers their whole repo, say plus external packages. So these are things that are installed on the system. Most of their build dependencies are defined that way. So you can see like CMake and AutoConf, stuff that they don't really want to bother building is in there. And they also have their compiler information and different package repositories configured in their environment. They're able to clone this thing and build the code from the environment and work on different components of it. What we're still working on is trying to build workflows around this. It's still not 100% clear how you should manage a poly repo for a project like this. And syncing pull requests among a bunch of different repos can be a pain. So we're trying to think of how we can deal with that. I don't know if that belongs in Spack or if that really is an external thing, but the goal is to switch this code over to Spack sometime in the first quarter of this year. Right now they have this alongside their older build system. Let's see. This is what it looks like. If you want to work with Marble, you'd clone their map repository with the environment. You can activate the environment, say what you want to develop, and then you can go and run the build. Spack will build it all in parallel on the cluster for you and coordinate through the file system. This can be shortened, so essentially, like there could be a default set or sets of things to develop within the environment, and that's it. So I guess I'll save questions till the end, but it was pretty cool to work with developers and to try to get a little more into their workflows and try to adapt Spack, which is really built for user provisioning on large machines for that use case. Okay, so the other thing that we did this year is we like I said, we gutted the old Concretizer and put in a new one. What the Concretizer does is it essentially solves all your dependencies. So I think people are familiar with how like APT or Cargo and other package managers have a dependency solver built in. Spax includes a lot of stuff that's not just versions. So you can solve for features, you can solve for compilers, you can solve for compatibility of build targets. So like we use ArchSpec for that. We can see if a particular package is compatible with what we're trying to build. And it takes a bunch of preferences from users. So developers can modify their, well, the Spack developers can modify the defaults in Spack. So there's some preferences that come from there. Admins have their own preferences that they have for a stack that they've set up. Users can have either environment configs. You can put stuff on the command line. And there's also constraints that come out of the package descriptions themselves. All that goes into the Concretizer and is used to come up with a consistent graph. That's what you're going to build. Typically, with Spack, if you have a particular revision of Spack's repo checked out, this is going to be the same thing is going to come out for the inputs that you give it. So if you install a particular environment and you keep your packages the same, like for a release, you get the same graph every time. What we were finding is that the greedy Concretizer was, you couldn't handle a lot of the build cases that we were dealing with. It would make decisions based on one package that weren't compatible with another because it would make the decisions too early. So we needed a full backtracking sort of NP hard solver. We have put in the new Concretizer in 0.17. It was experimental before, now it's the default. Essentially, we've written like an 800 line logic program that defines the semantics of Spack dependency resolution. And it looks a lot like Prolog. Answer set programming, it looks like Prolog, but it doesn't have operational semantics like Prolog. It's a little easier to think about. Essentially, it searches for what we call stable models, which are basically programs where all the rules are idempotent. If you infer something basically on the problem, it's not going to change. So you can think of it as kind of a fixed point solver, but with backtracking. What it looks like is this. So you have facts, like enable some feature is a fact. That's true. Node lamps is a fact. That's true. Node CUDA is a fact. That's true. That means CUDA is in the graph. Variant value lamps CUDA false means that the CUDA variant on the lamps package is set to false. And depends on lamps CUDA with the link means that you have a dependency from lamps to CUDA with dependency type link. You can put any facts you want in the program, but these are the ones that we use in the Spack solver. They just say this is true. You can have rules in ASP. So like the comma is like an and. This thing is like an if. And so what this is saying is if this node is in the graph, then we depend on a package with a particular dependency type. So if you had these rules, so if you had node lamps and depends on lamps CUDA link like this, then you derive that, come on, having trouble with the mouse here. Where is this? You derive that CUDA also has to be in the graph, right? So if CUDA has a dependency on lamps and, or if lamps has a dependency on CUDA and lamps is in the graph, then that CUDA has to be in the graph. Constraints say what can't happen. So you can basically do cool things like disallow cycles in 3 lines. So you can say that a path from A to B, there's a path from A to B if A depends on B. And if there's a path from A to B and B depends on C, there's a path from A to C. That basically defines the transitive closure of dependencies. And you can say that you can't have a graph where there's a path from A to B and from, oh man, I keep having this error, sorry. And from B to A. I'll edit this on the fly. There we go. This disallows cycles. And then the last thing that you have is you can give the solver a choice. So this is basically how we tell it how to make decisions. You can say if a package is in the graph, so node package, if, you can read this thing as if. The solver gets to choose, that's what these braces are, exactly one version, so at least one and at most one, from all the possible versions of that package. The capital letters are variables, so essentially these are filled in from facts that we tell the solver. Given all that, we can write a much more sophisticated logic solve, and it's also complete. So essentially, if there is a solution to a problem, then we will find it with ASP, which is nice. It can also be a little annoying because it's sort of like having a conversation with the most pedantic person you know. The solver will come back and say, hey, actually, you can resolve that this way. And it can come up with weird things sometimes that are technically what you asked for. And so in some cases, we find ourselves having to add more constraints to the problem, but it's a lot easier than modifying the code was before. What this has allowed us to do is add some pretty cool support for CUDA. So like we reworked the CUDA and Rock'em packages in Spack using this sort of general conditional stuff that we can do now. So previously, for example, like we couldn't do conditional variants. So right now, if you extend CUDA package in Spack, you have a variant called CUDA. There was another variant that was really only meaningful when CUDA was enabled, called CUDA Arch. And now we can basically say this variant only exists when CUDA is enabled. And we can reason about packages that way, and it's pretty simple to add this kind of thing. There's a conditional dependency on CUDA when that's enabled. And it's enabled us to express sort of the architecture support for the CUDA package. So by version, we can say this particular, when I need CUDA Arch 70, I have to have CUDA 9.0 or higher. And when I need 72, I have to have 9.0 or higher. And if I need 75, I need 10 or higher. And likewise, we can put all the constraints that CUDA defines on compilers into the package and have the solver reason about them much better. So if we're on x86-64 and CUDA is enabled and we're depending on CUDA at up to 10.2.89 on x86-64, then we need GCC at 9 or higher. Turns out on PowerPC, the version of CUDA that supports that version of GCC is actually a little lower, I guess. And so we can actually express that and differentiate between this version of CUDA on this platform and this version of CUDA on this other platform and the GCC dependency. There's a lot of expressivity in the DSL now with all these new conditional features. So and things that did not work before, like say enabling OpenMP on your BLAS when you depend on OpenBLAS, but not when you depend on other BLASs is a lot easier now. What the Concretizer has also enabled us to do is reuse installed packages effectively. And so this has come up at the Easy Build meeting before. I thought I'd throw in sort of a nice description of it. People say that Spack's hashes change. They don't really change. It's just that people like to pull the repo. I saw in Kenneth's presentation yesterday that most Easy Build users are using your release. And Spack has releases too, where we freeze the package versions. But most users seem to be undeveloped. A lot of them seem to just pull straight from the repo. And so really what's causing the hash changes over time is that you pull from develop, and the Concretizer is only looking at the packages that came from develop or that are in the repo. And when you pull, you're changing the default configuration. And so if you just say Spack install HDF5 before and after a pull, it's going to have a different hash because you had maybe a new version got added, maybe a default for a variant was changed. Anything can affect that, and we consider that a different build. And the way that we previously did reuse was we would take a resolved dependency graph like this. You could go and resolve that with the Concretizer. You'd create hashes for every node, and then you would basically say, hey, is this hash installed or not, right? And when you query the database in Spack for whether a hash is installed, you're looking for an exact match. And when the hash is changed, it's very sensitive, right? It will say, oh, I haven't built that exact thing that you asked for before, so I'm going to rebuild it for you. And so what this would lead to is when people pull from develop, they would get newer versions of packages over time, which is fine. They work. It's just that it's a waste of space, right? The old version that you have installed could be a fine replacement. So what we've been able to do with ASP is we can actually tell the solver about all the installed packages and their configuration so that we can make sure that all the constraints are consistent. So we can say, hey, OpenSSL is installed with this version. It imposes these constraints on the OpenSSL version that we resolve in the DAG if you pick this hash, right? And so what this is basically saying, here's a hash. These are all the properties of it. If you pick it, all of these have to be true for yourself. And the way that we optimize for that is actually pretty cool. You basically tell the solver that if a node for a particular package is in the graph, it can choose to assign a hash. It can choose to assign one of the installed hashes to that package. And so basically that's saying, I'm going to reuse that one. When that happens, we impose all the constraints for that package. And we basically just try to, we define built packages as ones that don't have a hash assigned, and then minimize builds. And so that's kind of it. That's the core of what we have to do to reuse installed packages. And so I thought that was pretty cool that it only took not as much code as I thought. What that gets you, if you look at the solve output, is here's Spack solve dash without reuse, right? And it's showing you what's installed over here. It said, oh, HDF5, well, you just pulled from develop. So I have to build like 16 or or well, like a lot of packages. I guess it's 20. So it's going to build 20 packages. And with reuse, basically it finds that 16 packages were actually acceptable for this build. Some of them, like OpenMPI over here, either weren't built before or just the installed version conflicted with what you asked for. So it'll build a new version, but it's going to reuse as much as it can. One thing we did find with this that was a little subtle is that you actually have to think about how to combine installed packages with built packages. Because if you look, there's actually 2 columns of criteria in here. These are all the optimization criteria that we have in the solver. If you just minimize the number of packages to build as your top priority, it does really weird things to your builds. The things that are already installed, it can reuse and it can pull them in and say, okay, I've got that version of that thing. But if you end up having to say build CMake, if you make minimization your top priority, it'll turn off all the options on CMake that mean that it would have another dependency. And so basically you'll get a CMake without OpenSSL or ncurses or other features that you would expect in a default install. So what we did to avoid that is we actually have 2 sets of optimization criteria. And basically if a package has to be built, then we prioritize sticking to the defaults more than reuse. But that's only once we find that it has to be built. So we sort of stratified the options that way. That took a while to formulate, but it's kind of cool. We learned that structuring optimization criteria is its own art in addition to writing a solver. So there's that. All right, and we tried this on pretty big package repos. So we took the E4S repository to see how the thing performed with lots and lots of packages. Let's see, what am I showing here? So for a package repo with like 6,000 cached packages, up to 63,000 cached packages, the solve time over here is taking mostly less than 10 seconds, which is pretty good. And for a small build cache, it's like less than 5. The setup, which is where we spend most of our time right now, is longer. And so, you can get up to 20 seconds on setup. This is basically reading the data into Python. And so there's a lot of work that we could do here to improve this. Essentially, we could cache metadata from packages and from the build caches better. And I think, this can come down. We were happy to see that the solves were actually not consuming the most time because we were worried that that could go exponential. So that was pretty cool. So for the roadmap, now that we have the new Concretizer, one of the things that we've wanted to do for a long time is to build dependencies and things that don't really require a fancy compiler with the easy compilers. So right now, Spack, if you try to install something, it'll try to match the compilers to what you asked for. And users can go and configure that, but it takes some configuration to say like CMake should be built with GCC and stuff like that. So what we'd really like to have is if you install something to run on the compute nodes, we want all the link dependencies and run dependencies of that thing to be installed with the fancy compilers. But we want the build dependencies to basically deal with something easy because they don't have to run in the backend environment. There's some cross compilation aspects to this that are complicated. So that's something that we can handle with the new solver. And the other thing that we want to do to make this easier is actually model things like, where is this? Hold on, did I cut out? Oh no, I skipped a slide. Okay, sorry. We want to model the runtime libraries of compilers and model compilers as dependencies. So right now, Spack compilers are kind of a configured thing. You can build compilers with Spack and you can say, hey, that compiler that I just built, I want to build with it. But you have to do the configuration of that yourself. We don't consider dependencies between compilers or dependencies on particular runtime libraries, which are essential for understanding compatibility. We do RPath things. So if you build with a particular compiler, we RPath its runtime libraries into the build. So you will get the runtime library that you want for your compiler. But what we can't do is compiler interop very easily. And we really want to be able to do this on El Capitan, which is the upcoming Livermore machine, because we will have 3 compilers in that environment. And we want to manage things like the OpenMP libraries and offload and ensure that the code teams can build with AMD, GCC, and Cray compilers if they want to in the same build. And it gets even more complicated with Rockham. Managing runpath and RPath across all those different installations and potentially vendored compilers is pretty darn complicated. And so what we want to be able to do is actually say like, okay, I installed this package number 2 here with the Intel compiler that depended on this version of GCC. It had a particular version of libstd C++. I installed this other package with a newer version of the Intel compiler and a different version of GCC. And I need to depend on that same libstd C++. What we'd like the Concretizer to do is say you can't do that because the 2 things are using different versions of C++, or if possible, configure the compilers to use a compatible version of libstd C++. This same problem comes up for OpenMP runtime libraries. So if different compilers have different implementations of OpenMP, or if one compiler has the bindings for, say, 2 implementations, but not for another, you can run into these weird runtime library conflicts. And so what we're going to be doing in right now is modeling compilers as dependencies, allowing them to sort of inject synthetic dependencies into the graph and say, like, here's the runtime libraries for the compilers that you're going to model, and allow them to provide virtual packages for the languages. So we want to, you saw the sort of the complexity in the CUDA package. It's actually a lot longer if you look at the real CUDA package, where the sort of CUDA arch level and the CUDA language level affect what version of GCC you can use. We'd like to just handle that with virtual dependencies, where the package says, I provide C++ in this version, or I provide these features of C++, and have the packages say what they need, as opposed to right now where we have to express all those sort of specific compiler version constraints across different compilers. So that's on the roadmap. The other thing that's on the roadmap is sort of continuing to build on CI. So we want to provide a public binary cache. We pretty much do right now. We have the builds for everything that we build in CI in one place. You could try to use it. Before we go public with it, we really want to make sure that CI is scaling so that the thing is reliable. And we want to ensure that the packages are signed in sort of a transparent way so that you can trust them. Those are the 2 things that we're working on. And right now, when Spack contributions come in from GitHub, we actually build them in a GitLab instance that's mirroring the Spack repo, and that reports status back to the pull requests. So far, we have been able to get basically every pull request building the core E4S stack on x86-64. We had ARM briefly, we took it down, and we're gonna put it back in. And then the University of Oregon has a bunch of pipelines, including a PowerPC one that we're building on a regular basis. At Livermore, we have runners that we are putting the containerized Cray PE on. And so what we're hoping to have there is actual CI for the Cray environment, so that we're building binaries for Cray all the time. Because actually building on a Cray is a giant pain, and it's hard to get right because of all the things in the environment. We've tried to improve that, and Cray has actually added a few things that have helped with that. So for example, we don't have to use the CC wrappers anymore. They have actual Cray CC compilers that are standalone in the newer PEs. And we had them put back the MPI wrappers that they had been butchering out of their Cray mpitch install, so that the system looks more like what you would expect from a standard build system. So with that, I think we'll be able to have much better portability to Cray environments. And then with CI, we'll be able to ensure that things keep building. Once this stuff is done, essentially every PR comes in, we figure out what needs to be rebuilt based on hashes in the pull requests. And every PR gets its own sort of binary cache that it can iterate on. So as you push commits, the builds are being done, and you can reuse stuff from prior iterations of the same PR. Once that's done in a sandbox with sort of a private build cache. Once it gets merged to develop and approved by a human, we go and rebuild it again on develop. And so the reason that we do that is because we don't want to allow stuff from an untrusted build environment, so basically any PR, to come into the public binary cache. So we sort of have this 2-level model where we're assured that we're at least building from some package that a human looked at in the main line, something that was approved. And so develop is sort of our standard for what we would trust. Whereas the PR, it needs maintainer review before we would trust it. We're going to put a signature in here. We're looking at SigStore and some other tools for doing that in a better way. I mean, we could put our private keys out there and just sign those binaries. Getting that right in CI is tricky, and so we're trying to look for a solution that would make that easier. And yeah, once this is done, once the PR builds, we get a status update on GitHub from GitLab that all the builds succeeded. This has been super useful for not breaking things. So whenever Adam Stewart goes and refactors, say, the whole Python stack, he can make sure that it builds on all of the different packages in E4S and at least a subset of the Python stack now. We still have some scalability issues. So Adam tried to add all like 1,500 Python packages to CI to see if we could do it. We hit some internal GitLab limit on the size of a pipeline. And so we're working with them on that and seeing if we can update that. But it is super cool to be able to have the binary builds running on all the different pull requests. It's been useful. Okay, so what we're really going for is lowering the burden of maintaining heterogeneous binaries for lots of different systems. And so if you can think of a traditional package manager with sort of a recipe per configuration, or like easy build with easy configs. Go into the build farm, you get sort of a one-to-one relationship of these binaries, although easy builds are obviously optimized, but there's a one-to-one relationship between binaries and configurations. And you get a software stack that gets upgraded over time. And this is not like easy build, this is more of a traditional package manager. With Spack, what we are trying to do is have this core set of parameterized build recipes that go into a build farm, and the same recipes are used for building all these different platforms. So we want optimized Graviton binaries, optimized Skylake binaries, optimized GPU binaries, and lots of software stacks maintained over time with seamless integration with source builds. And so that's really the goal, is to make sure that through things like Spack Develop or through building on top of existing packages with reuse, that we can, you get binaries for the core stuff, it's reliable. The binary builds are already done, and we mostly stick to that. But if you want to deviate, you can, and you can build the parts of the stack that you want. So we're trying to make that easy. If you look at the maintenance burden, or at least the code size of easy configs versus Spack packages, you can sort of see this effect. And if you look at the built-in Spack packages up here, we have about 6,000 packages. And it's like 162K lines of Python. This is from Clock on the repo. I cut out all the other crap below Python and diff, since both repos mostly are Python and diff. For easy configs, it's like 2,500 packages, although you could say that there are extensions in there, so that would get it closer. And I did this wrong. It is 449K lines of Python. That's the slide I was working on. And so, this is a lot more Python code to maintain. And the difference is that easy build has the configs versioned in the repo. Each one is a supposedly stable build configuration. And the trade-off is testing. What we're trying to do with Spack is really to pull out the configuration into the environment and into that lock file for reproducibility. So we have the configuration encoded there, and test lots of different configurations, but not put the burden of maintaining all the configurations on the package maintainer. So we really want to do more for the package maintainer and pull this stuff into automation. And I think that shows here, right? Like a lot of easy config maintenance is copy paste and replacement. And with the Spack packages, we're really trying to make it expressive enough to fill in all the parts of the software stack with a nice DSL. And one more slide. Yeah. The other thing that we're looking at is we have this research project on the side called Build. And we recently submitted a paper on this to MSR, Mining Software Repositories. Because the Spack packages are templated, we can go and come up with a way to sample the sort of combinatorial space of packages and try to build different things. And so we've done these models that we built from experimental runs of, like, say, audios, and then we tested it with different dependencies to see how likely the build is to work with different samples from sort of this matrix of builds. We have this kind of data for, I think we did 31,000 builds of different packages from Spack. It was like 60 packages, 31,000 builds. And we were able to show that we can actually predict the likelihood of builds we haven't tried yet pretty well. And so we're looking at taking this kind of model information and actually integrating it into the solver. So you can imagine that this sort of thing would go into the solver as a bunch of weights on different version combinations for things. And we could say, hey, avoid these ones. They're not likely to build, or they always fail, like this, whatever's happening with these wider parts of MPitch. And the hope is that what this would do is it would make things more likely to build if you haven't tried them before. So that's sort of the really long-term goal. But I thought this is a cool result from the research project, so I threw it in. And that's it. That's the state of Spack and the short and long-term roadmap. So any questions?
Thank you, Todd. I see that Kenneth has some questions, so I'll start with one of his.
Surprise, surprise. Yeah. When you were explaining the ASP stuff, I mean, and I think you've mentioned this before yourself. This stuff is pretty complex, right? To work on and to reason about and to getting the implementation right. So I think you spent quite a bit of time on getting that right, and it seems like at least now you found a good way to deal with it. I was wondering how many Spack maintainers actually work on this particular aspect of Spack, because I think it's quite complex. And as a side question, is there any negative effect on package maintainers, so the people who focus on particular installing particular software packages? So does some of that complexity leak into packages or not really?
Not the package maintainers see the DSL, right? And so they would see the conditionals. Really what's happened for the package maintainers, stuff like the conditional logic that they put in the packages works the way they expect now. And it doesn't do weird things because it went down one side of the solve and came back the other. So if there is a solution, it's complete. And they like that. Sometimes they'll see weird things, and we've been pretty quick about fixing them. Honestly, I think the fixes go in way quicker for the Concretizer now, because we have maintainers who can deal with it. And so it's me, Max, Greg, and Peter who are doing most of the core Concretizer maintenance right now. But like other folks at Livermore, like Tom and Harshita, even like folks at Sandia, have been able to pick it up now that it's written. I would say like it's way easier. Well, so like when I wrote the thing and when Max wrote the first version of it, I mean, we were coming from scratch, right? And like neither of us had ever done ASP before, or really Prolog. And I'd say that spin up time was a lot longer just because you kind of have to learn to program all over again. Once you see the solution, like it's very readable. You're like, oh yeah, that makes sense. It's coming up with it the right way that's hard. And so I think, you know, now that we have a core group of people who understand it, we can grow it. It's easier to maintain than the prior one for dependency solving, and it can do a lot more. And it's absolutely necessary for stuff like the separate concretization of build dependencies. There are some things that we would just not be able to do with the prior solver, the new thing. Does that answer your question?
Yeah, I think it does pretty well. And this is the Klingo third-party dependency, right? That you're now having to pull in and bootstrap. I've seen a couple of things fly by that this was painful. I'm not sure if it's still painful. Is that dealt with now? Like making sure that Klingo bootstrap is working well and it's not causing more trouble than it fixes?
The bootstrap binary I think it's worked well for most people, because I mean, we only released the new version in November. And according to the survey, like 50% of people are on the new Concretizer already, which I think is pretty good. The thing that it's a little painful for right now is error messages. So the error messages, they got worse in the sense that extracting an error message from an unsatisfiable core is not the easiest thing in the world, and it can be slow. So we're still working on that and trying to give people better pointers to where an error in a spec might be if the solution's unsatisfiable. But for the bigger environments, it was a huge help, because there were places where we just wouldn't find a solution before. So like for the visualization stack with all the OpenGL dependencies and things like that, and also for like all of V4S, it would just break and people would have to fiddle with it for a long period of time. And so now I think people find that they get a solution much more reliably the larger their stack gets.
Okay, and a different question I have is, since you mentioned error reporting, well, specifically for the solver, but one thing that has been a bit of an issue in Easy Build for a while, and that we want to work on going forward, is to have better error reporting. And with that, I mostly mean when a build fails, that you can pinpoint in the log file essentially what exactly went wrong. So usually pointing out the first compiler error, for example. So tracing that down is sometimes a bit of an issue for people. Does Spack have anything fancy there? Like pinpointing the first thing that goes wrong and pointing that out to people?
Yeah, we've done that for a while. We stole C-tests error regular expressions. And so there's actually a log parser. You can actually run Spack log parse log file and try it out on a log file to see if it works for you. It's got its own standalone command, but it runs on every build. And basically Spack will spit out the relevant section of the build with context with the error highlighted in red. And what we discovered, well, that was actually kind of fun because we put that in and then certain builds started taking 3 hours and we were like, why? And it was because the regular expressions in the parser were inefficient. So we had to go and tweak that a bit to make them actually not quadratic. But yeah, I learned a bit about Python's regular expression implementation and why Go doesn't do certain things that Python does.
But that only triggers when actually something goes wrong, or does it keep an eye on the output produced all the time?
It's streaming, so it's recording error messages where it sees them in the log. So okay. It's not just parsing the log after the fact. I guess we could change that. Maybe we should.
Yeah. Okay.
Yeah.
Yeah. Cool. Yeah, that's probably something we should take a look at and see if we can learn something there.
Those aren't the errors that we're. I mean, so the errors I'm talking about are ones.
Yeah, that's different. Yeah, that's the
These two
ASP
constraints
stuff.
Are different.
Yeah. Okay. We have some other questions as well. So Thomas, I'll just read it out loud. An obvious difference between EasyBuild and Spack is that EasyBuild defines an easy config file for a particular version of a library with a particular version of a compiler and dependencies and architecture. That's not really correct. Fine. Naively, this seems to make the CI testing easier since, well, everything is fixed, I guess. It either works or it doesn't. How does Spack decide what to test?
Yeah, I can show that. So, okay. The way that we decide, here, I'm gonna stop sharing, go over here, and pull it up. So here's,
and maybe while you're pulling that up, there's actually a related question also by Thomas. I guess the #1 priority for testing is governed by DOE ECP, like a major DOE application should build correctly on major DOE supercomputer. Is that correct? And does that influence the choices taken a lot?
I think it's really for the priority. We've had users add things. So here, I'll show you what we do. Maybe make this larger. Here's Spack. If you go into share Spack GitLab and under cloud pipelines, there's a GitLab CI YAML that defines what GitLab should do here. And then there are different stacks. And so right now we actually test 6 different stacks in CI. So one of them is E4S, one of them is E4S on Power. One of them is Livermore's own Radius stack. There's the Viz SDK. So this is all the people working on like ParaView and stuff like that. And there's our build systems stack, which is all of our internal build systems. And then this is actually Spack's tutorial itself. So we have binary packages for the tutorial, and we used to have to sort of hack on them every time we did the tutorial. Now we just build them in CI. So I'd say like the reason we chose E4S is really because it's like 500 packages, and it's one that people cared about. Because we haven't really, CI is not as stable as we would like it to be. And we still have scaling problems. We sort of decided to focus on that as our initial thing because it covers a lot of the HPC stack that people would care about. So if you look at this stack, it has a Spack.yaml in it, and it lists like some CUDA packages. So a lot of these are DOE packages, but I mean, they're things that people use, right? Really knows Tasmanian, Sundials, Raja, Petsy, MFM, Magma. I guess this may be pretty DOE heavy. I don't know what the easy build stack would look like if you had to pick sort of the canonical one. There's other specs down here for things that don't require GPUs. And basically we list them in here, and we have a little bit of config in the stack. This is basically how to map builds to runners. Anyone can actually contribute these. So like if you want to add a new stack to Spack CI, you can put another directory in here with a Spack.yaml in it and say that's the stack that you want to build. And what gets built in CI is determined by what this environment concretizes to. And so like this is maybe 90 packages right now as the roots of the environment. When we concretize it, it's like 500. And so and then essentially that stack is what we evaluate. We concretize it, we look at the hashes, and we keep building over time. Reuse is probably, we don't want to use reuse in CI. And so we will essentially, we're keeping the old strategy for the concretizer as well, so that when we want to do a completely fresh build from packages, we can, which is what you generally want in a CI build, test the latest thing. And if a user wants to reuse stuff, they can. So the idea is you build this, you throw all 500 packages in a build cache somewhere, or all, probably more than 500 packages because you're going to build it across different platforms and environments. You register the build cache with Spack and you install with reuse. and it'll prefer what's in the cache. And so you'll basically just be pulling from the binaries for the most part and building on top of it whatever you need for your project. Does that answer your question?
Well, it was Thomas's question, but then I think, yeah, I think it clarifies things. So how often do all these things get built? Is this like on every commit, on every PR, every day?
Commit, every PR.
So, let's say if I open a pull request to the easy build package in Spack, it's going to rebuild all these things.
No, it won't. We don't have easy build in our build stack right now, so it won't rebuild easy build.
Okay, but
it will.
Anything that's
it will
included
evaluate.
in...
It's gonna. So if you look at these, right, like here's Trillinos. You can go down to the checks on the PR, and here's the pipeline succeeded one. That takes you over to GitLab, our public GitLab, and here's the pipelines, right? These are all the Spack.yamls that we had checked in the repo, and these are the pipelines that get generated from them. And so GitLab has this feature where the parent pipeline can generate child pipelines, and so each one of these platforms generates its own pipeline. So like the E4S PR build should, if that Trillinos package actually changed, let's see, this is an annoying aspect of the GitHub interface or the GitLab interface.
So there is some relation.
Here's what rebuilt, right? It's only a part of the thing that rebuilt.
Yeah.
So it's looking at basically based on what changed in the package, it reconcretizes the environment. If it gets different hashes for things, it's going to rebuild those things. If it gets the same hashes for stuff, it's going to pull them in and say, I'm just going to install those from the binary cache. And the PRs can pull from either the sort of main like developed binary cache or their own that they can come from prior commits on the PR. And so mostly this is getting reused here. If it was the whole stack, you'd see a lot more. But this is basically everything that depended on that Trillinos change. That's getting rebuilt in that PR. So that's how we keep it manageable. I guess the other thing that I could mention is that we are changing, now that we have reuse, we're going to make the Spack hash much more granular. So previously we omitted things like build dependencies from the hash. Because it would mean that people would have to rebuild for every new version of CMake. Now we're going to include that and a hash of the package.py file. So essentially we're going to get a lot more detail in the metadata for Spack. And that'll help CI because this is one of the scaling problems with CI right now, is that actually like E4S does have packages that require different versions of build dependencies and they come up with the same DAG hash, even though they really are different builds. And they fight over spots in the build cache because the current deployment hash that we use is too coarse. So we're working on that. That's our current priority for CI is basically making the hash granular enough for all this stuff.
Yeah, it's a pretty cool setup. And as long as you're making sure you're only really rebuilding what's relevant, let's say, I can imagine this is somewhat manageable. I mean, we're all sitting on top of a supercomputer, so resources is usually, hardware resources is usually not our biggest issue.
The cool thing here is, so actually, like, you can go to HTTP and note that it's HTTP because they didn't bother to set it up, stats.e4s.io. And the E4S folks are maintaining this stats page for our CI. So you can see like that we've done 500,000 jobs or so in CI since we started, I guess, in September. And you can see what percent is building at Oregon versus AWS. So actually, like we're not running on Livermore resources. We're running on public Oregon resources because Livermore, at least, we have the CI things that we're trying to set up with the Cray environment. And those are in sort of a green zone where we would allow untrusted builds. The Oregon folks don't really care, I guess. And so they let the builds run there. And in AWS, we basically have both Oregon and AWS runners. You can actually see like Oregon's node descriptions here. There's a link off. These are all the machines that they have. And so they've got like Intel GPUs and AMD GPUs and NVIDIA GPUs and stuff. And this is all sort of under ECP that they were able to get this sort of, they call it Frank for Frankenstein cluster. This is basically last 4 hours. We prefer the Oregon runners, so you can see that if it's not loaded, then we'll just stay there. And if the Oregon runners are busy, then we'll go off to AWS and build. And so this is showing like for all time, what percent of jobs ran at Oregon versus AWS. So the idea is really, we'd like to add more runners to this. I think it would be cool to take the CI setup for Spack and sort of generify the backend. Right now it generates GitLab CI, but there's no reason it couldn't generate GitHub Actions. It's just that we because a lot of these builds take time, we didn't prioritize that because it's, the builds will just fail after 6 hours unless you put your own runners on them. And so now that GitHub CI supports custom runners, we could do that and do this in GitHub Actions. I think we'd hit a whole other set of scaling problems there. But you could imagine, you could take the back end and farm it out to whatever build system you wanted. It would be some coding, but it's doable.
Yeah, you can also
GitLab was also chosen, GitLab was also chosen because a lot of the DOE sites are using GitLab internally, and so it made a lot of sense for internal code teams to use this kind of CI.
Yeah, for GitHub, you could implement your own GitHub app and just use that to listen to pull requests and have a big fat Slurm cluster as a backend. But
well, and actually, we started with plain GitLab mirroring, but we have a bot now that manages kicking off the pipelines. You can tell the bot to rerun the pipeline, so you'll see people say SpackBot run pipeline on PRs. That turns out to be necessary because just managing the commits and where the merge commit is generated and things like that between the CI systems is complex. And so GitLab's native CI, I think, is designed for a much smaller use case than this. And so we're sort of pushing the limits of that too.
You also mentioned that in AWS, you had to turn off the ARM runners, essentially, or the ARM pipelines.
We didn't have to. Those are maintained by someone at AWS, and they ran out of time to work on that. So once they're done tweaking that stack again to their liking, we'll turn it back on. We figured if they weren't actually using the pipeline, we'd turn it off while we waited for our scaling to get better. We need to look at how to reduce AWS costs because getting the right runners, using spot instances where we can, ensuring that we don't use a whole giant Skylake node when we do a Skylake build, things like that need work. Right now, the way that we do this is there's several pools of AWS instances. They cost nothing to keep running. They're just the Kubernetes cluster on the back end. And we hook the Kube cluster up to GitLab as an auto-scaling runner. And basically, if you look at that pipeline, you can see basically if we match LLVM or LLVM AMD GPU, those two packages. This is ROCm CC because AMD has brilliant naming schemes that are very descriptive. And this these get mapped to this container image and a huge instance, which is mapped on the back end to some sort of AWS instance. And these packages get mapped to an X large. These packages down here get mapped to a large and so on. So essentially you match on the Spack spec, and then you say what kind of runner you want to build it. And so for all the 500 things that are getting built in the environment, it runs through these matchers and says, oh, I should put that on that builder. So this is basically just how do you map Spack's descriptions of builds to resources. Yeah.
And so the ARM thing was just a separate stack that was listed. So please also test these things on ARM.
Yeah, so the power stack is basically the E4S stack with a bunch of tweaks for power. You could do it as a separate stack. You could work it into the same stack if you wanted to. I think people have found that managing the stack separately is nice because the configuration is ever so slightly different. Yeah, so there are pull requests you could look at where people just add another subdirectory here, right? And it's another Spack.yaml. So if you look in here for the power runners, there. It's looking for a PPC 64LE instance or really a runner tag. And only University of Oregon has these runners, so this will get run on an Oregon machine. So GitLab has both UO runners and a Kubernetes cluster hooked up to it from EKS. Yep.
Okay. Yeah, I think that goes into quite a lot of depth on how the CI is done. Yeah, it's interesting.
Yeah. So the hope is, I would really like to be able to maintain a binary distribution just from pull requests, because I think most binary distributions are sort of maintained in developer spurts. And I think if we could pull that off, it would be really cool. Okay, the idea is rolling release on And so like essentially if you clone develop for Spack, you would be likely to get binaries for whatever is current. That two-phase thing is a little complicated there because like if we didn't have this trust issue, then you could just move the binaries over to the public cache when they get merged. And there would always be binaries available for develop, but because of the rebuild, we lag. So I don't know if we need like a staging area or something where it doesn't quite get merged to develop after the PR is approved until the rebuild's done or something like that. We'll see. But the idea is have a rolling release on develop and then have stable binaries for every major Spack release as well, so that you can go back to that, run those.
Yeah, that sounds like a big challenge to me, especially if you also have different targets, let's say, and which is probably going to get worse. You're already dealing with x86 and power. You've played with ARM. That's not going to get better going forward. But, yeah.
RISC-V. Yeah. We have some people interested in RISC-V right now, so I think that, yeah. And we need Mac builders. That's the other one that we haven't tackled yet. We don't have a Mac pipeline at the moment.
Mm-hmm. That's also in AWS, so if you can get the.
Yeah, they are. They have. I think with our volume, it wouldn't matter, but you kind of have to. I think you have to hold the Mac runner for a longer period of time. Like the allocation for instances, it's like you have to keep it for
building chunks. Yeah. But you don't have to keep it, but you're paying for it anyway. Yeah.
That, yes. So we'll have to work on that.
Yeah. Okay. I don't see any other questions popping up. So if anyone does, please raise your hand or mention it in Slack. But I think we're ready to wrap up. Thanks a lot, Todd.